Hi everyone, my name is Marc-Antoine Moinnereau. I am currently doing my PhD in the MUSE laboratory at INRS, which is located in Montreal, Canada. What I would like to present you today is Saccadic eye movement classification using ExG sensors embedded into a virtual reality headset. The presentation is organized as follows. First of all, I will introduce the goal of this project and the motivation. Then I will talk about the materials and methods, followed by the result we obtained, and finally the conclusion we reach in this study. So let's start with the introduction. Recent projections suggest that the global augmented and virtual reality market has generated revenue around $26 billion in 2018, and it is expected to reach approximately $800 billion by 2025. A large part of this growth will be in consequence of the implementation of the 5G network, which promise wider coverage, lower latencies, faster speeds, and more stable connections. These advances will increase the sense of presence and the perception of immersion it provides to the user. They are indeed the most important factors for the success of VR immersive application. On the other hand, eye tracking has emerged as an interesting modality to increase the sense of presence in VR by making interactions more natural. However, camera-based eye tracking devices usually rely on infrared cameras and they are expensive for VR. Therefore, we highlight in this study the use of a DIY wireless solution for saccadic eye movement detection based on the low-cost ExG sensors and the low computational load. In addition to gaze information, the measurement of saccades from ExG can be very useful. It can be correlated to the sense of presence and to the detection of emotion. Moreover, it is also possible to measure blink rates from ExG, which can be very useful in predicting cyber sickness. Therefore, for the reason I just mentioned, we are highly motivated to detect saccades directly from ExGs. So to achieve this purpose, we propose the use of two conventional classifiers and a new hierarchical classification approach to classify the saccadic eye movements into 36 directions in VR. To achieve satisfying classification performance, we explore the use of two popular feature extraction methods. So, in this study, we want to answer two questions. First of all, what feature is optimal for the task at hand? And then, what classification methods is the best? I am now going to talk about the materials and methods that we use. The prototype is presented here in the lower figure. We had certain requirements for the ExG signals measurement system that we wanted to use. The bio amplifier had to be portable, low cost, light, and also have a wireless communication capability. Therefore, we selected the OpenBCI amplifier, which provides 8 input channels. We propose 7 ExG electrodes to record eye movement that are embedded directly into the foam of the VR headset. These are flat dry electrodes from the Saud technology company. 3 electrodes are located near FP1, FPZ, and FP2. There are also 2 horizontal electrodes as well as 2 vertical. And the data was streamed using the open source Mule software. The type of eye movement we are interested in detecting in this study are the saccades. Saccades correspond to a rapid simultaneous movement of both eyes in the same direction. In this figure, the red line corresponds to the stimulus. It indicates the position of a fixation target, and the blue line corresponds to the movement of the eye. So, when the target moves suddenly from the center of the field of view to the right, there is a delay of about 200 milliseconds before the eyes begin to move to the new target position. and the duration of the saccade is typically between 30 and 120 milliseconds. The experiment is quite simple, as can be seen in the figure. Each participant was asked to visually focus on a target that moved from the center of the field of view to the one of the 36 position on the screen, which correspond to 10 degrees over circumference. They repeated the task 6 times, and also to avoid blink and facial muscular artifact. Each time the target moved back to the center, the participants had a break of few seconds to rest and blink few times before the target moved again. In order to have usable and efficient data for the classification task, the ExG signals have to be first pre-processed, and then we can apply one of the methods for feature extraction. As it is in the literature, ExG signals were bandpass filter between 25 and 125 Hz and zero mean normalized. The data were then epoched into a 1.6 seconds segment. So now we can apply a feature extraction algorithm. We decided to first use the time series analysis HCTSA toolbox to extract statistical features from the ExG epochs. It gave us 7,664 features per epoch. As there is a lot of redundancy in these features, we applied the minimum redundancy maximum relevance feature selection algorithm to select only the most relevant one feature for each channel. As there are 7 channels, we have the top 7 for each epoch. The slope-based features has also been explored as feature extraction methods. The figure here displays the average of the 7 ExG signals when the participant was looking up, down, left, and right. So as can be seen, the patterns across the 7 signals varies from different eye movements, especially with respect to the slope of each signals. For example, for the up and down direction, the frontal EEG channels, which are FP1, FPZ, and FP2, show opposite slope signs, and similarly for the left and right direction. The slope can be expressed with the following formula, where M is the slope, VAV is the minimum valley amplitude, PIV the maximum peak, VAP the position where the VAV value is located, and finally PAP the position where the PAV value is located. So in total, 1 feature per channel is computed for a total of 7. To classify the saccadic eye movement, we use 2 conventional classifiers, a multi-layer perceptron neural network and a support vector machine classifier. To train the SVM, we used the classification learner toolbox from MATLAB with default hyperparameters. For the MLP, we used the deep learning toolbox in MATLAB. The network was trained using the scale conjugate gradient methods, and the hidden layer was empirically fixed to 10 hidden nodes. So finally, a 4-fold cross-validation was performed with 75% of the data were used for training and 25% for testing. We propose to use also our own classification approach. As can be seen in the figure, this classification is performed in 4 steps. The first 3 levels correspond to a series of binary classification tasks, and the last level to either 4 or 5 class tasks. The first level aims at discriminating if the user was looking at the upper or lower quadrants. The second level discriminates from the right and left directions. Thus, the combination of the first 2 levels provide details about which of the 4 quadrants the participant was looking at. Then the third level classifies the upper and lower half of the 4 quadrants, which give to us one of the 8 regions. And finally, the 4 level aims to classify to the nearest 10 degrees. To summarize, 14 classifiers were used in this architecture, and we decided to test it using both SVM and MLP. So I will now present the result. If you remember, one of the questions in this study was about the feature importance. The figure here shows the relative importance of the top 20 features that were selected most often from the 7,000 statistical features of the 14 classifier. So I will present the top 3 most important features. First, the statistics on local segments show to always be important as it is present in 12 of the 14 classifiers. For the horizontal EOG left and the vertical EOG left channels. It is based on sliding window along the time series and measuring some quantities such as the mean, standard deviation, and so on. Then the normalized nonlinear autocorrelation, it showed to be the most relevant for the vertical EOG right, FP1, FP2, and FPZ channels. Finally, the time series properties variation always show importance for the FP1, FP2, and FPZ channels. Its goal is to apply a given pre-processing transformation to the time series, which can be polynomial or sinusoidal, and return statistics. About the classification accuracy, as can be seen in the table, we compared our hierarchical classification approach to a non-hierarchical classification methods using either SVM or MLP classifier. The results are presented for each feature type and also the combination of both via feature fusion. So while for the hierarchical classification approach, the first 3 levels correspond to a binary classification task, and the level 4 or 5 class task, we have on the other hand for the non-hierarchical approach, for the level 1 to 4, it corresponds respectively to a 2, 4, 8, and 36 class task. Moreover, we also explore a scenario in which errors that are off by just 10 degrees are not counted as error. It corresponds in the table to the level 4 with an asterisk. So the table presents the average classification accuracy and the standard deviation obtained across each cross-validation trial for all participants. So as can be seen, SVM classifier always outperform MLP. Then the hierarchical approach almost always outperform the 36 class approach. Feature fusion in turn showed to improve classification accuracy, thus suggesting feature complementary. Furthermore, it was found that the majority of the errors were made with one-step neighboring classes. So the classification accuracy in level 4 star increased substantially for all feature type and classifier. Therefore, to answer our second question about the classification method is the best, the hierarchical methods with SVM classifier and the fused feature set showed to be the best approach, achieving an overall accuracy of 76.51%. Well, this brings to the end of my presentation. To conclude, this study has taken the first step to validating a low-cost DIY solution based on embedding ExG sensors directly into the faceplate of the VR headset by exploring 2 different kinds of feature type and 2 classifiers. It was found that with as low as 7 ExG electrodes, 7 features, and a series of simple linear SVM classifier, we could achieve an accuracy of 76.51% on the 36 class classification problem. So we show that accurate saccadic eye movements can be tracked in a low-cost manner with a low computational requirements. And these are important factors for real-world application. So thank you for watching, and don't hesitate if you have any question to email me.